Hello everyone, today our team will present a project on image caption generation using a CNN transformer architecture. This project focuses on automatically generating text description for images using state-of-art deep learning. Over the next few minutes, I'll walk through our motivation, model design, training process, results, challenges, and further improvements. The main goal of the project is to build a system that can look at an image and describe it in a natural language, just like a human. Image captioning is more important for accessibility, image retrieval, and automatic content generation. Traditional captioning models have used CNN for further feature extraction and LSTMs for text generation. But now, transformers have become the best option because they understand long-range dependencies better. So, our work combines a CNN encoder with a transformer decoder to achieve high-quality captions. In the literature, many approaches try to bridge the gap between visual understanding and natural language generation. The early models relied heavily on recurrent networks like LSTMs. However, recent papers show that transformers provide better performance mainly because they process text in parallel and capture relationships more effectively. Several works also highlight the importance of large datasets like MS-COCO. Our project builds on these ideas and extends them with our own architecture and training pipelines. Model architecture. This is a core architecture of our project. We use a pre-trained CNN, specifically a ResNet-based encoder, to extract features from the image, and the CNN converts each image into a dense feature representation. These extracted features are then passed into a transformer decoder, which uses multi-head attention to generate captions word by word. The decoder looks at both the image features and the partial caption to predict the next token. This encoder-decoder design allows the model to produce meaningful content-aware captions. Our method follows a clear pipeline. First, we pre-processed MS-COCO image and captions. Then, we tokenize the captions and create a vocabulary of 10,000 words. Images are resized and passed through the CNN encoder. Then we train the transformer decoder on the caption sequence. During the training, the model learns to map visual features to text descriptions. And inference time, we use greedy decoding to generate captions. For training, we use MS-COCO dataset, which is a standard dataset benchmark for image captioning. From this dataset, we use 80,000 images, each with 5 captions and 10,000 word vocabularies. MS-COCO is an ideal because it has diverse real-world sentences and detailed human-written captions. This helps the model learn a wide variety of objects, sentences, and sentence structures, improving generalization. We train the model for 25 epochs since transformers can be heavy, and we used efficient batch sizes and learning rate rescheduling. The CNN encoder was partially frozen to speed up the training and maintain stable gradients. Overall, our training pipeline ensures the model learns both visual and linguistic patterns efficiently. Model hyperparameters. Here are some of the important hyperparameters we used: image processing, transformers, and training, with each embedding dimensions, number of attention heads, decoder, layers, maximum caption length, dropout rates based on the recommendations from the related research. These settings helped us to balance the performance and the training time. Training results. Our model achieved strong training performance. The training loss reached 2.35 and the validation loss was 2.22. The training accuracy was 52%, while validation accuracy slightly improved to 54%, indicating good generalization. We also achieved CIDA score of 0.912, which shows competitive performance for captioning tasks. Here are some sample predictions for our model. In the first example, the model has a pasta and vegetables on the table, which closely matches with the ground truth. A plate with pasta and vegetables on a wooden table is generated, and the ground truth here is a dish of pasta with fresh vegetables served on the table. And in the second image here is correctly identified. A dog is playing with a red ball on the grass, and the dog playing fetch with a ball in the park. And in the third image captures a person riding a bike on the street, and the ground truth, a cyclist riding a bicycle on an urban road. These examples show that the model understands the object's relationships and produce grammatically correct captions. These are some of the things we have tried and we have implemented. And the GUI application, we also built simple GUI application which looks like this, and this interface will allow users to upload an image instantly and generate a caption, which we'll be showing in our demo. And the interface makes the model easy to use and demonstrates its real-world application. This adds an interactive element and turns the model into a working tool rather than just a research prototype. And here are some settings given here, and the key techniques. Some of the key techniques we used are transfer learning, like the pre-trained mobile NetV3 on ImageNet provides robust image features without training from scratch, and teacher forcing using ground truth tokens during training for faster and more stable training. Attention mechanism, which is a cross attention which allows decoders to focus on relevant image regions for each word. Repetition penalty. This prevents the word repetition in captions by penalizing already used tokens. And now here are some of the challenges and the solutions we have for them. The challenge for long captions is the COCO captions exceeded 50 token limit, and the solution for this is increased max caption length to 80. And the second challenge is word repetition. Model generated repeated words, and the solution to this is added repetition penalty of 1.3. The challenge for this is memory issue. Full COCO dataset, it is too large, and the solution to this is limited to 80k image subset. Another challenge was caption diversity. Early outputs were repetitive. We solved this by tuning dropout, increasing training epochs, and improving tokenization. One challenge was the training time, since transformers required a lot of computation. We solved this by freezing part of CNN and optimizing our pipeline. We can also make some further improvements by using vision transformers instead of CNNs, adding beam search for nuclear sampling for better captions, and using larger data sets. We can also deploy the model as a web application or a mobile app for broader usability. To conclude, we successfully implemented CNN transformer architecture for automatic image capturing. Our model provides semantically consistent and grammatically correct captions, and it performs well against benchmark metrics. This project demonstrates the strength of transformer based on decoding and the benefits of combining it with CNN feature extraction. Now I'll show you the demo of our project. Here, after running that command, we can find this is a GUI here, and you can upload and now it's generating the captions here, so it's generating it correctly. And this is launching the GUI again. These are the both things. Now we can select a different image. Right, so here you can see the generated captions here. It's like all the colors here is displayed on this. This is how our project works. This is the UI of our project, and we have used a small data set to train it, and the accuracy here is built, as I have said before, the accuracy is almost 80% of the accuracy. You can see the results. And this is what we have successfully completed and implemented the CNN transformer architecture for this image captioning, and the models we generated were semantically accurate and grammatically correct and effective transfer learning from pre-trained datasets. And this is our project about image caption generation. Thank you.